Okay, so for this very last video, I'm just going to go through these miscellaneous examples that try to incorporate aspects of a function, the derivative, and the second derivative all at once. And so in this first example, it says f of 2 is equal to 4. That's just a point. F prime of 2 is equal to 0. That tells us the slope of our original function at x equals 2 is equal to 0. So I'm going to have potentially a relative extrema right there, horizontal tangent line. And then my second derivative is negative, and that's for all x. And try to remember that second derivative, especially when they're talking about positive and negative, is giving you information about the concavity of the function. So putting those couple pieces together and actually thinking about what we were just doing with the second derivative test, if you're concave down and you've got a place where the first derivative is equal to 0, then you might even be thinking right now what kind of relative extrema x equals 2 would be. But let's sketch this out and see if we can visualize this. And so I've got the point 2, 4. So 1, 2, 3, 4. And so here's my point. And I know that the derivative is equal to 0 here, and that the function is always concave down. So I guess when I think of a concave down function, a lot of times I think of functions that kind of look like this. But remember, just because it's concave down doesn't necessarily mean that it's got to go up and down. It could be that. It could also be just this piece. But in this case, we do know that at x equals 2, we have a place where the first derivative is equal to 0. So chances are we do in fact have a function in this example that looks something like this. And I think this is it, because you've got f of 2 equals 4. Check. The first derivative at x equals 2 is 0. And you could see that we've got that horizontal tangent line at x equals 2. So we check that box. And our second derivative is always negative. We're always concave down. So that's what you would do in this very first one. Let's go to example B. So very similar. We start off with f of 2 is equal to 4. So let's get that back on there. So f of 2 is equal to 4. So we're going to be going through that point. And again, we have the first derivative is equal to 0 at x equals 2. And so we might be thinking again, something like what we were doing before, but the concavity changes a little bit. And so we've got two pieces here. One piece is our second derivative is positive when x is less than 2. And so that means our function f is going to be concave up when x is less than 2. And then our function is going to be concave down when x is greater than 2. So we need to somehow think of how we can draw this where we're going to have a horizontal tangent line at this point, and then we're going to go from concave up less than x equals 2 to concave down when x is greater than 2. And so a lot of times, people would look at this with concave up and they would say, okay, well, if it's concave up, then it's got to go something along the lines like this. But if you do that, you're actually approaching like what would be an infinite tangent line, or maybe not infinite slope on the tangent line at x equals 2, but you're approaching a large slope. And what do we want the slope of our function to be at x equals 2? We want it to be 0. So we're not going to start with an increasing concave up function. So let's just erase that and let's try again. So the only other thing that we can do is, if we're going to be concave up and increasing didn't work, we're going to have to try concave up and decreasing. And so this right here looks, I'm trying to sketch something where it's sort of concave up still. Remember, concave up does not necessarily have to be completely that way. It can simply be that, or it could just be this type where you're increasing. But I think this is actually going to make more sense, because can you see when this is coming down that at x equals 2, it looks like we could set this up where we are going to have a horizontal tangent line. And then on the other side, we want to be concave down. And if we're going to be concave down, we have to think, how are we going to be concave down? And we most likely want to connect to this point right here because you know, we could see that our derivative does exist at x equals 0, and so if I made a jump, then that wouldn't make sense. And so if I'm going to connect to this point and then be concave down, probably going to just do something like that. So I think that this x equals 2 is actually a point of inflection. We could see that the concavity is changing. The second derivative is changing sign at x equals 2. We've also got our horizontal tangent line right there. And we've also got our point 2, 4. So this is what this graph would look like. And that's kind of how you want to go through these types of examples. But I hope I've gone through enough in the notes here. This is exactly what I would have gone through in the notes in class. And I think now you can hopefully do the homework in WebAssign. Let me know if you have any questions.